evening and welcome to the Sleeping Zoo. Facts to fall asleep to. The story of the salmon is not merely a tale of migration, but a profound biological odyssey that challenges our understanding of survival, sacrifice, and the interconnectedness of global ecosystems. To look upon a salmon is to witness a creature that exists as a bridge between two worlds, the freshwater arteries of the continents and the vast saline depths of the world's oceans. This journey begins in the shallow, oxygen-rich gravel of a stream, often miles from the nearest coastline, where life is cradled in a nest known as a redd. Within these pockets of stones, thousands of translucent orange spheres represent the future of a genus that has survived ice ages and tectonic shifts. The initial phase of their life is defined by the alevin stage, where the tiny fish remain tucked within the safety of the gravel, still attached to the yolk sacs that provided them with their first source of sustenance. As this internal pantry is exhausted, the fish emerges fry, possessing a newfound hunger and a territorial instinct that belies their minuscule size. They must learn to navigate the currents and avoid a gauntlet of predators, from kingfishers to larger trout, all while preparing for a transformation that is as much chemical as it is physical. This transition from the sheltered stream to the open ocean is governed by a process of staggering complexity known as smoltification. It is here that the salmon undergoes a cellular-level overhaul to prepare for the high salinity environment of the sea. For a freshwater fish, the salt of the ocean is a lethal dehydrator, but the salmon has evolved a way to reverse its internal chemistry. During smoltification, the fish's kidneys undergo a massive shift in function. In the stream, their bodies are saltier than the surrounding water, meaning they must constantly expel excess water while retaining saltwater. Once they reach the estuary, however, the environment becomes far saltier than their internal tissues. To survive, their kidneys must pivot to a mode of extreme water conservation, and specialized cells in their gills, called ionocytes, begin to actively pump excess sodium and chloride out of the bloodstream and back into the ocean. This physiological pivot is accompanied by a change in appearance. The dark, mottled camouflage of the stream-dwelling parr is replaced by the shimmering silver scales of a smolt. This silvering is a form of countershading, designed to make the fish nearly invisible to predators in the sun-dappled waters of the open ocean, where there are no rocks or logs to hide behind. The miracle of the salmon's journey is not just that they survive the ocean, but that they can find their way back to their precise point of origin years later. This feat of navigation relies on a sophisticated sensory suite that functions like a biological GPS. Scientists have discovered that salmon possess a geomagnetic map within their brains, likely aided by microscopic particles of magnetite. This allows them to sense the Earth's magnetic field, providing them with a sense of latitude and longitude while they roam thousands of miles through the North Pacific or Atlantic. As they approach the coast, a second, even more refined sense takes over: their olfactory memory. During their initial descent from the stream as smolts, the fish undergo a process called imprinting. They literally memorize the unique chemical signature of their home waters, a bouquet of minerals, soil types, and decaying vegetation that is specific to one single stretch of gravel. Their sense of smell is so acute that they can detect a single drop of their home water diluted in millions of gallons of seawater. They are essentially following a scent trail that spans an entire hemisphere, guided by a biological imperative that overrides every other instinct. Once the salmon returns to the river of its birth, its body begins a final tragic metamorphosis. Having spent years gorging on the rich bounty of the ocean, like shrimp, krill, and smaller fish, the salmon ceases to eat the moment it enters fresh water. Its entire digestive tract begins to atrophy as the body redirects every ounce of energy toward the development of eggs and milk. The physical changes are dramatic, and in many species quite haunting. The sleek, silver athlete of the ocean transforms into a rugged, colorful warrior. In the sockeye salmon, the skin turns a brilliant, bruised crimson, while the head becomes a vibrant green. Males of many species develop a kype, an exaggerated, hooked jaw filled with sharp teeth used for competing with other males for the right to fertilize a nest. This process is essentially a fast-tracked aging. Their skin thickens, their immune systems begin to fail, and their organs start to shut down. They are the living dead, fueled only by the fat stores accumulated in the deep sea, pushing themselves up waterfalls and through rapids with a singular terminal focus. The death of the salmon is not an end, but a massive infusion of life into the surrounding terrestrial environment. This is the foundation of the marine-derived nutrients theory, a concept that has revolutionized our understanding of forest ecology. When a salmon dies in the headwaters of a mountain stream, it brings with it a concentrated package of nitrogen, phosphorus, and carbon that was harvested from the depths of the ocean. This is essentially a massive upstream transfer of energy against the pull of gravity. Research has shown that up to 80% of the nitrogen found in the needles of Sitka spruce and Douglas fir trees near salmon streams comes directly from the ocean, delivered by the carcasses of fish. This is tracked through the presence of nitrogen-15 isotopes, which are far more common in marine environments than in terrestrial ones. Scavengers like grizzly bears, bald eagles, and wolves play a crucial role in this distribution, dragging carcasses deep into the woods. A single bear might pull dozens of fish into the undergrowth in a single day, eating only the high-energy brains and skin, and leaving the rest to rot and fertilize the forest floor. In this way, the salmon literally builds the giant trees that shade the streams, ensuring that future generations of fry have the cool, protected waters they need to survive. Beyond the biology and the ecology, the salmon occupies a sacred space in the human story, particularly among the indigenous peoples of the Pacific Northwest. For the Haida, Tlingit, and Coast Salish, the salmon are not merely a resource, but a distinct race of beings, or salmon people, who live in great longhouses beneath the sea. According to myth, these beings choose to take on the form of fish to offer themselves as food to humans, but only if they are treated with the proper respect. This spiritual contract is celebrated in the first salmon ceremony, a ritual that occurs when the first fish of the season is caught. The bones of this fish are carefully preserved and returned to the river, facing upstream, so that the spirit of the salmon can return to the ocean and tell its kin that the humans are still worthy of their sacrifice. This perspective stands in stark contrast to the industrial view of the fish that emerged during the 19th and 20th centuries, where the salmon was seen as an infinite commodity to be canned and shipped around the world. This clash of perspectives has led to a modern crisis in salmon conservation. The construction of massive hydroelectric dams throughout the 20th century turned raging rivers into a series of stagnant reservoirs, blocking the ancient highways the salmon relied upon. While engineers attempted to solve this with complex concrete staircases designed to help the fish bypass the dams known as fish ladders, the success of these systems has been mixed. Even more controversial is the hatchery versus wild debate. In an attempt to bolster declining populations, humans began breeding millions of salmon in concrete raceways. However, these hatchery fish often lack the genetic diversity and survival instincts of their wild cousins. When they interbreed, they can weaken the overall resilience of the population, making the fish more susceptible to disease and less capable of navigating the rigors of the migration. Today, restoration efforts have shifted toward more holistic approaches, such as removing obsolete dams and replacing narrow culverts that act as miniature blockades. These projects are an admission that the salmon's survival depends on the health of the entire watershed, from the smallest mountain seep to the widest estuary. We are learning that to save the salmon, we must save the river itself, acknowledging that this silver traveler is the heartbeat of the land. To understand the sheer physical resilience of the salmon, one must look closely at the hydrodynamic challenges they face as they ascend a river. A salmon's body is a masterpiece of fluid dynamics, evolved to minimize drag and maximize thrust in high-velocity environments. When a salmon encounters a waterfall, it does not simply rely on brute strength. It utilizes a phenomenon known as the Kármán vortex street. By sensing the tiny whirlpools and eddies created by rocks or fallen logs, the salmon can actually capture the energy of the moving water, flicking its tail in a precise rhythm that allows it to slingshot off the current's own power. When it comes to leaping, the physics are even more precise. A salmon can leap up to 12 feet into the air, but this requires a specific depth of water at the base of the falls. They use a rapid start swimming motion, building up immense kinetic energy in a deep pool before breaching the surface at an angle of roughly 60 to 80 degrees. The tail continues to beat, even in the air, a vestigial effort to maintain momentum, until gravity brings the fish crashing down into the upper pool. This is a high-stakes gamble. A single miscalculation can result in a fatal impact with the rocks or a loss of energy that the fish cannot afford to replace. Once the salmon reaches the headwaters, the focus shifts to the creation of the redd, a process that is a masterclass in geomorphology and microchemistry. The female salmon selects a site not by sight, but by feeling the flow of water through the gravel with her fins and belly. She is looking for an area of downwelling where oxygen-rich water is pushed down into the stones to provide a constant supply of air to the buried eggs. To build the nest, she performs a rhythmic digging motion, turning on her side and flapping her tail vigorously. This creates a low-pressure zone that lifts the silt and smaller pebbles, allowing the river to carry them downstream, while leaving a depression of clean, heavy cobbles. The chemical environment within this nest is fragile. If too much fine sediment settles into the redd, it can suffocate the eggs by blocking the flow of oxygenated water. This is why the health of the surrounding forest is so vital. Trees stabilize the banks and prevent the runoff that leads to siltation. The female may lay several thousand eggs in a series of these pockets, each time moving slightly upstream to allow the displaced gravel from the new hole to cover the eggs in the previous one. This engineering ensures the eggs are buried deep enough to avoid predators, but shallow enough for the fry to eventually emerge. While the Pacific salmon of the genus Oncorhynchus are famous for their one-and-done life cycle, the Atlantic salmon of the genus Salmo possess a different, perhaps even more complex, survival strategy. Unlike their Pacific cousins, Atlantic salmon are iteroperous, meaning they can potentially spawn multiple times. After the grueling ordeal of the first spawn, a small percentage of these fish, known as kelts, manage to survive the winter in the river and return to the ocean to feed and recover. The physiological strain of this is almost unimaginable. A kelt is a shadow of its former self, thin and silver dark, having lost up to 40% of its body mass. Yet, if they reach the salt water, their bodies can once again undergo the reversal of the smoltification process, healing their organs and regaining their strength for another journey. This rare ability to return multiple times provides a genetic insurance policy for the species, ensuring that even if one year's migration is decimated by drought or flood, the older, more experienced survivors can return to replenish the population. This endurance is likely why the salmon features so prominently in the mythology of Northern Europe. In the Celtic tradition, the salmon is the ultimate symbol of wisdom and secret knowledge. The most famous of these tales is that of the salmon of knowledge, or the Bradan Fisa, which lived in the River Boyne. It was said that this fish had eaten 9 hazelnuts that fell into the well of wisdom from the overhanging hazel trees, thereby absorbing all the world's knowledge. The prophecy stated that the first person to eat the salmon would gain this wisdom. When the poet Phineagius finally caught the fish after 7 years of trying, he tasked his young apprentice, Fionn mac Cumhale, with cooking it. While turning the fish over the fire, Fionn burned his thumb on the hot skin and instinctively sucked on it to ease the pain, unintentionally becoming the recipient of the salmon's infinite insight. This story illustrates a profound cultural recognition of the salmon's journey, that by traveling to the ends of the earth and returning, the fish brings back something of the other world to the realm of men. The modern industry of salmon farming has attempted to replicate this life cycle within the confines of floating sea cages, but the ecological cost has been a subject of intense scientific scrutiny. Large-scale aquaculture creates an environment that is ripe for the spread of parasites like sea lice, which can bloom in the crowded pens and then spill out into the surrounding waters, devastating wild smolts as they pass by on their way to the sea. Furthermore, the concentrated waste from these farms, from excess feed and feces, can lead to localized eutrophication, stripping the oxygen from the seabed and altering the local marine chemistry. The debate is further complicated by the issue of escapes. When domesticated Atlantic salmon escape their pens in the Pacific, they threaten to compete with native species for habitat and resources. The science of genetic pollution is a major concern for conservationists, as the escapees can interbreed with wild populations, potentially diluting the locally adapted traits that have allowed wild salmon to survive in specific river systems for 10,000 years. The restoration of salmon runs is now being viewed through the lens of connectivity science. It is no longer enough to simply protect a single stream. We must protect the entire corridor. This includes the restoration of estuaries, which act as the critical waiting rooms where salmon acclimate to the changing salinity. In many urban areas, these estuaries have been paved over or industrialized, leaving the fish with nowhere to hide from predators or rest during their transition. Innovative projects like breaching the dikes in the Pacific Northwest are working to reconnect these tidal wetlands to the main river channels. By allowing the tide to once again flood these areas, we are creating the nutrient-rich nurseries that young smolts need to put on the weight required for their ocean journey. The return of the salmon to a restored waterway is often the first sign of a healing ecosystem. When the fish return, the insects return. When the insects return, the songbirds follow. The salmon is the lead actor in a planetary drama of recovery, proving that if we provide the path, life has an incredible capacity to find its way home. For decades, the period of time a salmon spends at sea was referred to by biologists as the black box. Once the smolts vanish into the salt-crusted horizon of the North Atlantic, or the vast gyres of the North Pacific, they enter a world where human observation is nearly impossible. Here, the salmon undergoes a radical physiological shift. In the ocean, they become apex predators of the mid-trophic level, feeding voraciously on capelin, herring, and sand eels. Their growth is exponential. A fish that left the river weighing a few ounces can return weighing 30 pounds or more. This growth is fueled by the cold, nutrient-rich currents of the subarctic, particularly around the Faroe Islands and West Greenland. However, the ocean is also a landscape of shifting thermal boundaries. Climate change is currently redrawing the map of these feeding grounds. As the cold pool of the Bering Sea shrinks, or the Atlantic meridional overturning circulation fluctuates, the salmon are forced to travel further north to find the specific temperatures of between 4 and 10 degrees Celsius that their metabolism requires. This increased travel distance burns critical fat reserves, meaning that even if the fish survive the ocean, they may arrive at their home rivers with insufficient fuel to complete the upstream journey. The true miracle of the salmon, however, is not what it takes from the ocean, but what it brings back to the land. This is the science of marine-derived nutrients. When a salmon dies in the headwaters of a mountain stream, it is effectively delivering a package of fertilizer from the deep ocean to the heart of the forest. Scientists have tracked specific isotopes of nitrogen and carbon that are unique to the marine environment. These isotopes have been found in the needles of Sitka spruces, in the fur of grizzly bears, and even in the feathers of songbirds miles away from the water. In a very real sense, the trees of the Pacific Northwest are built from the bodies of fish. When bears and wolves drag salmon carcasses into the woods, they eat the high-fat brains and roe and leave the rest to decompose. This nitrogen-rich organic matter is then processed by a hidden army of invertebrates and fungi, eventually being absorbed by the root systems of the forest. Research has shown that trees along salmon-bearing streams grow up to 3 times faster than those along barren rivers. In return, these giant trees provide the shade that keeps the water cool and the fallen logs that create the complex pools salmon need for resting. It is a perfect, closed-loop biological economy. To safeguard this economy in an era of rapid environmental change, a new field of techno-conservation has emerged. One of the most striking examples is the salmon cannon, or whoosh passage portal. This system uses a flexible, pressurized tube to safely transport salmon over high dams that were previously impassable. Using computer vision and AI, the system can identify the species of the fish in milliseconds, sorting native salmon from invasive species and shooting them gently into the upstream reservoir. Further down the technological rabbit hole is the use of environmental DNA. Instead of catching fish to count them, scientists can now take a single liter of river water and sequence the genetic material shed by the organisms within it. This allows for the detection of salmon populations in remote or inaccessible areas, providing a real-time map of biodiversity without ever touching a single fish. We are also seeing the deployment of acoustic transmitters, the size of a grain of rice known as smart tags, that allow researchers to track individual salmon across thousands of miles of open ocean, finally beginning to illuminate the secrets of the black box. However, technology is only a bridge. The ultimate survival of the salmon depends on our willingness to respect the ancestral rights of the river itself. This has led to the burgeoning movement for the rights of nature, where rivers like the Magpie in Canada or the Wanganui in New Zealand have been granted legal personhood. Under this legal framework, a river is not just a resource to be exploited, but a living entity with the right to flow, to be free of pollution, and to sustain its native species. For the indigenous peoples of the Salmon Coast, from the Haida and Tlingit of North America to the Sami of northern Scandinavia, this is not a new concept. It is a return to a worldview that has existed for millennia. To these cultures, the salmon are not just stocks or biomass. They are the salmon people, a sibling nation that provides for humanity on the condition of mutual respect. As we look to the future, the story of the salmon becomes a story of resilience in the face of the Anthropocene. We are seeing salmon pioneer new territories. As Arctic ice melts, Atlantic salmon are being found in the Beaufort Sea, and Pacific salmon are appearing in the Canadian Arctic. They are a species that refuses to give up, constantly probing the edges of their environment for a new way forward. The question is whether we will provide them the space to adapt. This means removing the dead capital of obsolete dams, a movement that saw its greatest victory with the ongoing removal of 4 massive dams on the Klamath River, the largest dam removal project in history. As the concrete falls and the silt clears, we are witnessing a prehistoric homecoming. The rivers are remembering their old paths, and the salmon, guided by an internal compass we are only beginning to understand, are following those paths back into the mountains. The saga of the salmon is more than a mere biological trek. It is one of the most profound acts of sacrifice and renewal found in the natural world. Every year, millions of these silver travelers respond to an ancient chemical call that pulls them from the vast, salt-laden expanse of the open ocean back to the specific, gravelly cradles of their birth. They swim against the relentless current of gravity itself, leaping over falls and evading the keen claws of predators, driven by a singular, inherited purpose. By the time they reach their spawning grounds, their bodies are battered, their scales transformed into the vibrant reds and deep olives of a final, glorious costume. In the act of laying and fertilizing their eggs, they exhaust the last of their energy, ensuring that the next generation begins life with the protection of the very stream that once nurtured them. Yet, even in death, the salmon's journey is not over. Their decaying bodies become a monumental gift to the terrestrial world, a pulse of nitrogen and phosphorus that fuels the growth of towering ancient cedars and feeds, a complex web of life, from insects to eagles. In this sense, the salmon is the ultimate bridge between the sea and the soil, a silver thread that sews the ocean to the forest. For the indigenous cultures that have revered them for millennia, the salmon is not just a resource, but a relative, a sacred guest who arrives every season to sustain the people. This relationship serves as a stark reminder of our own responsibilities in an era of shifting climates and dammed rivers. To protect the salmon is to protect the health of the entire watershed. It is to ensure that the ancient song of the river continues to find its rhythm. As the final ripples of the season's spawn fade into the mountain mist, the cycle begins anew, a testament to the resilience of life and the beautiful, brutal symmetry of nature. The story of the salmon teaches us that every ending is a beginning, and that in the grand tapestry of the wild, no journey is ever truly lost, so long as the waters continue to flow. Thank you, and good night.